Happy morning to all.
రావట్లేదు.
Listen, sir. Welcome to the today's session, Day 2 webinar on recent trends in materials chemistry organized by Department of Chemistry, RGUKT-R. So hope all the participants enjoyed the yesterday session. So yesterday the first talk was given by Dr. Narth Nikishore sir on nanomaterials, its introduction, synthesis and applications, followed by Dr. Jayaprakash sir, given talk on organic covalent-based molecules for CO2 capture applications. And in the today session, in the today track, we have two more wonderful talks by two energetic and effective speakers, namely Dr. A.V.R. Reddy Garu and Dr. S. Raghupatrao Garu. And our first session is going to start with the talk of Dr. A.V.R. Reddy sir, and he is going to give his talk on chemical safety, safety measurements in laboratory, so which is one of the important topic for each and every chemist and also for all others, because in our daily life we are using so many chemicals in both in kitchen and for cleaning and also particularly in institutions. So sir going to give a talk on how to handle with these chemicals in our daily life, which may be helpful for all the users. So now it's time to invite our energetic speaker, A.V.R. Reddy Garu. So A.V.R. Reddy sir started his career in 1977 at BARC in the nuclear chemistry section, and he did his PhD in nuclear fission, and continuously he did his postdoc in Main, Germany, and he worked in various levels in BARC, Mumbai, as a head in nuclear chemistry section till 2008, and he also worked as a head for analytical chemistry division till 2015. Because of his enthusiasm towards the teaching, he is also worked as a professor in Vikram University, Nellore, and currently he is a CEO for Gemological Institute of India, Mumbai, and his interested areas of research are nuclear fission, most related to nuclear fission, nuclear reactions, nuclear analytical techniques, electroanalytical chemistry, and environmental science. And he has about 700 publications in reputed international journals, and he has co-authored 4 books and edited about 32 books. And he is the active member of many scientific associations and editorial board member of 2 international journals. And apart from all this, he is very interested and energetic speaker. So he is always ready to share his knowledge with all types of faculty or institutions, etc. So he is given more than 400 lectures in throughout the India and also in abroad like Asia, Europe, and South America. So these are the few words about Dr. A.V.R. Reddy sir. And with the short introduction, I'm inviting A.V.R. Reddy sir to give his valuable talk on chemical safety. So over to you, sir. Welcome to the session, sir.
Good morning.
Very good morning, sir. So all the participants are eagerly waiting for your valuable talk.
Good. Let us hope everybody will be happy.
Hope they will definitely enjoy your lecture.
So when you order, I will open.
Yes, sir.
So should I share now?
Yes, sir. Yes, sir. We are making.
Okay. Okay.
My co-host.
Share screen. Yeah.
Sir, yes, no, you can present, sir.
No, I am trying to share. Is it seen?
Yes, sir.
So I put on.
Yes, sir. Yes, sir. Now your presentation, we can see your presentation, sir.
Okay. See waiting room. That's your job, no? See waiting room.
Yes, sir. So we will admit them, sir. You can carry on with the presentation.
Okay. That is the thing. When you say I will start.
Yes, sir. Now you can.
Good morning to everybody. Am I audible?
Yes, sir.
I need not use the speaker, right?
Yes, sir. Your voice is very clear, sir.
Okay. Good morning to everybody. I will be talking about chemical safety, both safety as well as good laboratory practices. I'll just give an introduction. So accordingly, my plan of talk is like this. First, I will go with uh, uh, definitions, that is safety, chemical safety, QA, QC, GLP, etc. Then I will explain as I have written here, and particularly a bit of emphasis will be given on GLP. Then I will go with the chemical safety, that is safety in a chemical laboratory, which is relevant particularly for the students, teachers, and researchers. And one of the things I will be explaining you the meaning of RAM and what is responsibility. I will just show unsafe and unsafe conditions and unsafe acts. Then what all you practice on chemical spillage, I will show you just introductory. Then I will spend some time on materials safety data sheets, which is very important. In fact, students can take it as a project, which I will explain. Then often confused terms, hazard and risk, I will explain. Then fire and explosion will be explained. Then one of the things is green chemistry. Many have some misconcept that it is the solution for every ill. No, I'll just briefly touch upon. Then how to dispose chemicals safely. And we have set up one incineration facility in BRC. I'll just do the principle. Then some procedures we developed to dispose potassium cyanide safely, I will share with you. Then of course, Vizag gas leak, I will explain you how GLP was not practiced, how it led to this disaster, I will explain. At the end, I will talk about attitude and behavior, and if time permits, and if the participants are in a mood, I will review Bhopal gas leak, but not a must. This will be the part of my lecture, which I feel 50 minutes to 1 hour, 10 minutes, it should be over. But I would like to have more questions rather than completing the syllabus. Because I plan with 2-3 modules as 2-3 modules. So if we don't complete one module, it's okay. Better to exchange information among the participants. So I thought, because most of the participants are students, I thought I will explain you the meaning of learn through questioning and sharing. Because this was not originally included, I thought for students it is of much use. This acronym KCRSD I made, and most of the places where I go to universities, I explain this. And in fact, the first two, K and C, were explained to me by my teacher, that what am I seeing, put a question mark, then why is it happened? If we know that much, then we will understand that something is happening. That curiosity has to sustain to know, to reason it out. When we understand, we can share with classmates by collectively discussing, and finally convince colleagues and teachers by giving a lecture or demonstration. So I always believe in collective learning as it is faster, and it is true for any subject, including chemical safety. Before I proceed further, I want to tell questioning is the most important to learn. And in fact, when I was a 8th class student, I wrote a small couplet, and I would like to share because majority of the students might be Telugu people. Prashna చదువుల తల్లి అడగందే అమ్మాయినా పెట్టదు, అడగందే అయ్యవారు చెప్పరు, అడిగి తెలుసుకోండి ముందుకు పండి అంటూ ఏదేదో రాశాను. But what I want to convey is questioning is important. Since there are many teachers who are delivering the lectures, it is better to allow the students to ask questions, encourage them. Their thinking is focused in the process we learn, because I believe a teacher learns more than the taught. But at the same time, when a student prepares, do not get pressurized. Remember poem, plan, organize, plan a task, organize that into small subtopics, execute them. If the result is as you expect, be happy. Otherwise, replan and monitor. This monitoring is important. Plan, organize, execute, monitor, replan. That's all the thing. So in life, we can achieve. So it is true with the learning of anything, as well as even chemical safety, in an industry, preparing for an exam, anything, a bank accounting, anything and everything, or walking on a road, everything we plan inadvertently, but plan systematically. That is my appeal. And everybody will be comfortable, but never get pressurized. So, okay, now come to the topic, safety and chemical safety. This all of you know, but I just want to read. Safety is freedom from danger. That's all the thing. In danger, injury, or damage. If chemicals are involved, we call it chemical safety. That's the thing. These definitions all of us know. But the last para, what I wrote here, is important. We achieve safety with a ramp approach. What is ramp? Recognize hazards, which we can do in advance, but need not be 100% correct. Be able to assess how hazards might occur. Make an effort, an individual makes an effort to minimize and plans to manage. This is RAMP, R-A-M-P. And thus, one can control hazards with an ultimate aim of minimizing the risk. That's an important thing. So let us follow how to achieve the safety by RAMP, because all the students work in the laboratories with chemicals, even the yesterday's lecture, material science or MO, organic frameworks, and afterwards lithium battery, and so on. So everywhere chemistry. I will show one projection for that. So material science, medicine, environment, everything. Therefore, chemical safety one should know. So it is essential to prepare work-related quality assurance and quality control and good laboratory practices and documentation, which we normally miss, Asians in general. And we have to make document and implement strictly. Like when we go into the laboratory for a qualitative analysis, we carry a procedure, right? And that sort of thing everywhere we need. And at the same time, we need not cut the intuitive thinking and towards research. For research also, it is very useful. I'll show you. So before we proceed further, I just want to share with you one slide or two slides. What is QA/QC? See, normally we follow this QA/QC day in and day out. For example, if you purchase a pen, we first sign and see whether it is writing properly or not. So in our mind, we know that if it moves smoothly, that is the quality we are looking for. And how are we controlling? We are controlling by seeing the property. So without realizing, for example, you are purchasing a mango, we just see the aroma or flavor, or we touch it whether it is ripe or not. So all the things we do with experience. But what I advise is fruits okay, pen is okay, but when we are doing around laboratory or doing in an industry, we better have a document. What was missing in Vizag thing was document was in place but not followed. So we have to better keep the document and follow. One is document that explains the quality requirements, and following is quality control, and assuring that everything is followed is quality assurance. Now, quality is just a numerical set of desired properties of an object. You call it a chemical, you call it a mango, or whatever it is. So specifications that are fit for an intended purpose. If you talk about a mango, eating is the final desire. If we talk about a chemical, the quality, is it a pure compound, right? If you are producing a product, is it the pure compound? If you are talking about a medicine, is it fit for the purpose? And so on and so forth. So we are now looking for COVID vaccine, but recently Johnson & Johnson announced that it did not serve it was not fit for the purpose. Therefore, there will be a delay. So the fit for the purpose is whether it is useful on the test objects. That is the people. In the case of mango, it is for us to eat. And in the case of a chemical, when you prepare a standard solution, it should give expected molarity or normality. So now, to just list the requirements, what is QA/QC, I have written here, all of you can read for yourself. This is to assist laboratory personnel in the case of your university for students. If you have researchers for the researchers, identify and minimize sources of error. This is an important aspect. Use standardized procedures. Suppose if you want to prepare a sodium hydroxide solution, you should have a protocol. Right? You may do research later, but in the beginning, this is required. Documentation is very important, as I repeatedly tell, and implement it. Effective utilization of resources is an important. Many people consider QA is a wastage of time, wastage of resources. No, I totally disagree. This is an important thing in the long run. You save time, money, and everything, and quality is maintained. Minimization of non-conformances. Any deviations are there, get back to that and see what is non-conformance and rectify it. Internationally, it is acceptable. This is the thing. If you want to publish in a very good journal, even you talk about nanomaterials, they look at the procedures, what procedure you have followed. And once you refer on a procedure I have followed, then they will not spend time on that. So even for an acceptability internationally, not only material, even research publications, we have to maintain this QA/QC, or you have to certainly inform that you have followed these things. So it is very useful in research too. That is the point what I want to emphasize. QA/QC is not once for all and be done. It is a continuous process of evaluation, learning, and implementation. Even what you think is a precise measurement today may not be precise after 20 years. What we thought when I was a student, that we cannot have a measurement better than a nanogram. Now we can have, because of directly or indirect methods. So what we think today may not be applicable after a few years as far as quality and detection limits are concerned. Therefore, we have to go on evaluating this quality aspect and document, and improvements we have to put as new versions and implement ultimately. So this essentially increases the awareness. So what are good laboratory practices? This is another word many people have misunderstanding. Actually, it has started by FDA essentially towards the medical application of medicines and medical aspects due to some accidents or deviations. So instead of going into history, GLP is a standard procedure for conducting work in a laboratory. It consists of implementation and monitoring, and essentially observations are recorded, reported, archived honestly. That is very, very important. Okay. So benefits are development of quality test data. For students, it may appear a bit tough, but it is very simple. International acceptance of data, I already explained. helps avoiding duplication of data. I tell you, once you come into research, even yesterday, Kishore might have noticed our MOFs. There are so many duplications of works. As a member of funding agency, I used to cut down duplications, but then effort has to be made by the individuals, not by the authorities. Aimed at removing technical barriers to R&D. This is an important thing. As I told you, for example, if you want to publish very fast, just inform that you have followed certain procedures which are acceptable internationally, and automatically it will be published. And for applications, and most importantly, protection of human health and environment. In the cases where we are at the concentration levels are at the decision levels, particularly in the case of human health and environment. Everybody talks about environment, but most of the people do not know what is decision limit. Once we are clear about it, because GLP, we can contribute
Excuse me, sir. Sir, your voice has been muted, sir. Sir, you have to unmute, sir. Sir. Sir.
Are you not listening? Hello?
Yes, sir. Now, okay, sir. Previously, your voice was muted, sir.
You want me to continue?
Yes, sir. Now continue, sir. Now your voice is audible.
Say go back.
No need. Okay, sir.
No, where?
Just,
Which
uh,
slide?
the starting of this slide, sir.
From the beginning, you did not listen.
No, sir. Just a few seconds only. You're muted, sir.
Okay, I'll go to previous slide. Okay.
Right.
So I was explaining you about what are good laboratories.
Yes, sir. No.
Huh? And this is essentially observations are recorded, reported, archived. You know the meaning of it. So I won't spend time. But benefits are plenty. Development of quality test data, international acceptance of data. I explained about the publication in good journals. Helps avoiding duplication of data. This is very, very important. I will repeat. I can repeat n number of times this part because, again, I was telling you yesterday, Kishore, and those two talks, nanomaterials and MOFs, particularly MOFs. People write anything and everything and claim that they will solve the environment problems, and they do with a carbon dioxide cylinder and leave it there, publish and leave it there. No, you have to see the end results. I used to be a member of DST as well as Board of Research in Nuclear Science. These projects I used to be very critical because you have to see the end results. Similarly, energy sources, energy, battery development, solar systems. People write anything and everything and publish beautiful papers. But the question is application will be missing. That's why we have, if we can avoid duplication and focus the resources on a mega project with multiple participants, we can discover many things and have applications. So to avoid duplication, this GLP is important. Honesty is important. Aimed at removing technical barriers to R&D, this I already told. Protection of human health and environment. Let me repeat again. When we have to make a decision, that is the decision limit, and all of you know, I suppose, if you are dealing with the decision limits, particularly applicable to human health and environment, it is better to understand whether we have reached a decision limit or not, so that this will be helped by GLP and it protects human health and environment. Let us not confuse the people and talk like, irresponsible newspapers, right? There are quite a few newspapers which are irresponsible, talk about environment, but we have to be, being scientists and academics, we should be responsible and contribute the reliable data. For that, we need GLP. GLP is part of QA/QC, aimed at developing and implementing quality systems, and it's very crucial. So now if you proceed to, I just want to share with you what Horowitz has written, a great analytical chemist. In 78, he published a 3-page paper, which I have given reference here. He calls GLP as internal honesty and integrity. And in fact, I met him in Hungary in 1999. He's a really gem of a scientist. And he shares, you just see here, quotes, unquotes. One of his colleagues, he tells, because of our preoccupation with truth, that is, research aim is to find out the truth. We have difficulties with issues concerning half-truths. This is the problem. Hurrying, publishing in a hurry. This issue doesn't stop politicians, lawyers, or government bureaucrats, but not the scientists who act on these matters frequently that affect us. But scientists and academics, we have a responsibility to look at the truth, not the half-truth. And his gist of his view is that 3 pages I wish most of the teachers get a chance to read. I gave the reference here. Many view GLP as unnecessary, prohibitively expensive, enormous paperwork, low productivity, and above all, monotonous. Actually, this is not true. None of them is true. To begin with, yes, and impediment to creativity is absolutely wrong statement. That is the general feeling. I view it as a matter of common sense and above all, having internal honesty and integrity. So once you write, see, we were told in our MSc by a teacher that if you write the data in the laboratory, don't overwrite, cut it and rewrite. Sign there why you have cut it. This is an important thing. That is internal honesty. And integrity to say that I have done this mistake. Of course, in a common instrumental methods. Okay. So GLP is concerned with safety and process control. As far as we are talking about chemical lab, be it industry or a research lab, 6 parameters we have to control: methodology, reagents, standards, sample. I think all the students know this. When you do a titration, we need a standard, we need a sample, we use a reagent, particularly here an indicator, and method we follow. But don't forget that environment, workplace is very, very important. It should be clean. And above all, attitude of the analyst or researcher or the student. This is very important. These are the 6 parameters we have to control. And let me share with you, you cannot avoid chemicals. It is no research. It's not a big discovery. Everybody knows it. You talk about environment, you talk about energy materials, physics, material science, which you are listening to, medical sciences, anything you talk, chemistry is an important link. It deals with the materials, that is chemistry. And everywhere you have to measure what is the value that you use. So analytical determination and instrumentation are very important. Therefore, you need QA/QC, you need GLP. So chemistry, you just cannot avoid, just you cannot close the boxes and keep quiet, right? In whichever area of research, there is a common interaction among all the subjects. And what is that? Can we avoid? No. Chemistry is an experimental science. Chemical work is linked to society's progress, hence it continues. One of the greatest innovations of the last century, you all know that polymerization and plastics, though now we don't like because they are not degradable, but there are solutions that improved our quality of life. That is the point what I want to tell. Quality of life has been improved by many discoveries, and one of them is this polymerization. Helped in reducing volume, weight, and increased longevity. And for example, what happened in Vizag, polystyrene that was useful for styrene and polystyrene, unbreakable plastics, micro-oven vessels, and so on and so forth. But starting materials are something like styrene, right? You all know, I need not spend time on polymerization. So it brought along a few safety and environmental issues, and these issues we have to address, we have to be careful, and it is our responsibility to apply all these innovations safely, reap the benefits, and take care of the environment. Please mark these words. We have to use them safely, we have to reap the benefits, and we have to take care of the environment. No responsible person suggests to throw the material. we use the word dispose. There is a difference between throwing and disposing. Unfortunately, 90% of the people are throwing the material. Now, I want to remember Mahatma Gandhi here and Einstein. Is it good to avoid working with chemicals? Because it may result in fire, accidents, deaths, and deals with hazards and toxic chemicals, creates chemical waste, etc., etc., etc. No, we have to deal with them. And answer is no. And you just see anyone who has never made a mistake, has never tried anything new. This is the great physicist of last century, Albert Einstein. So better to do something and take care. And remember Mahatma Gandhi, strength doesn't come from physical capacity, it comes from an indomitable will. If we have the will, we can carry on anything. So better to be careful, understand the things, follow ramp, use chemicals, get the benefits safely, and take care of environment and the people. Learn lessons from the past events, analyze, document, and don't repeat, and move on. And here I want to tell, after Bhopal gas tragedy, lots of documents are made, but unfortunately, Vizag accident took place. Only thing is, number of deaths are much lower, but nevertheless, it happened, which is absolute recklessness of not following the international standards. Though it is an ISO company, which I will share with you in the last. So, use of chemicals unavoidable. As I told you in the beginning, accidents can occur in the education labs, research labs, industry labs, and anywhere. So better is we gather the correct information before using chemicals. That is MSDS, I will explain in the next slide. Plan to dispose waste safely. This point is very important. Don't throw everything in the sink. Depending on the chemical, depending on its material safety, this is material safety data sheets. And after getting every detail, if we are satisfied, there are certain chemicals that can be added to municipality wastage, that is a tap water. Otherwise, you have to store and dispose. Documented GLP to be followed. For that, we have to make a GLP based on this, good laboratory practice and document. Follow it safely and we won't contribute to nuisance. Adhere to safe ethics. Hopefully, no waste generation, but I don't believe, but minimum waste generation. Because waste will be generated. Even when you take the food, there will be a plate, there will be something. When we clean, there will be wastage. Therefore, we have to minimize it. And important thing is training, continuous education, evolution of safe practices. Believe me, in 1999, at the age of 47, I attended a training program arranged by ISO to understand. Already we were implementing. That is why that program title also was called Training for the Trainers. So a continuous education to update ourselves with the latest developments is very important. Training is the hallmark, be it in teaching lab, be it in research lab or industry. Now, what is an accident? I don't think I have to explain this, right? So accident is a potential for physical harm. It is there is an event that has the potential for physical harm to persons or property. And this red you see mainly caused by human error or high risk conditions. Because if you have absolute an industry, iron industry, I don't know how many of you have seen in Madhya Pradesh now, Rayagad, we have a steel plant. If you go there, there is a definite chance somebody gets exposed to heat radiation. But be careful. That's all the thing what we have to do. When you are cooking food, there is a possibility that we touch the hot plate with hand. So avoid, use a spatula. It's the question of how to use it. When we cut a fruit, definitely knife can cut our finger also, but we don't stop cutting the fruit. We are careful while doing that. That's why we have to be aware about the possible accidents and take safe work. Unsafe acts and unsafe conditions lead to accidents. You follow a ramp, automatically this will be minimized. And possible unsafe conditions in a chemical lab, all of you know, gas cylinders is one of the major things. Don't forget that glassware is equally dangerous, because if you break glassware, it can cut anywhere and everywhere. And fire, of course, you use the Bunsen burner just like that, but be careful. Electricity, this is the thing normally we care, we don't care much. And radiation, definitely it will cause, but I worked in radiation for 40 years, nothing happened to me. You have to be careful. And of course, chemicals. These are all unsafe conditions. There may be a few more. And how to, and just see this unsafe act. I'm sure most of the labs don't have a first aid box. If you have, I'm very happy. Then housekeeping, this is the thing many people violate, just like that. Accident reporting, that is the thing where I call internal honesty and integrity. Many people just avoid and run away. Not many, a few. Labeling, when you prepare, this is the first thing I used to teach my juniors, that whenever you make a solution, please label it, write your name with the date. And layout of the lab, I'm sure 70% people don't keep it, particularly in teaching class. Right? It is better to keep the layout and outside the wall so that people know where they are going. And waste management. This is another place, as I was explaining earlier, we should have a policy for waste management. Be it used chemicals, be it used electrical ware or instrument, etc. We should have a policy how to dispose them. Now, yesterday Kishore was talking about preparing the nanomaterials bottom up and top down. And you also know the meaning. As far as the chemical safety and responsibility is concerned, these two approaches are in vogue. I always believe it should be bottom up. That means junior most person should follow. Once everybody follows, automatically entire safe. Hello? You want to say something? Okay. So this bottom up is very, very important. For example, keeping our country clean. It is unfortunate a prime minister has to talk about it. It's a wastage of time because he has many jobs. But we are not following. That is the problem. Suppose you keep your lab clean and your surroundings clean, automatically your village will be clean, then your town will be clean, your district will be clean, state will be clean, nation will be clean. Prime Minister need not spend time. So what I'm telling is, all of us follow the things strictly at our level, automatically cleanliness is maintained. Responsibility should be with us. We have to follow. So bottom up is important and we should follow. Top down is okay. When we don't do properly, then a prime minister or a chief minister will order. We follow. But bottom up is important. But in a teaching lab, it is to begin with is a top down, because a teacher has to explain and put an order, then everybody has to follow. So both the things are applicable. Particularly bottom up is good when the moment you become a researcher. So I developed two acronyms, EEEM. Establish first all the rules, educate juniors, empower them to work, but monitor. That is the responsibility. This is important. So EEM. Suppose some deviations are observed, don't howl on the juniors. Follow AAR. What is that? Analyze the incident, identify the problem, act on it if the person is responsible, act on it to solve it clearly first. Then if the person is irresponsible, reprimand. But don't start shouting. Mistakes can happen. All of us might have done the mistakes. So being seniors, particularly this is applicable for top down, it is not the authority to issue an order. It is to help develop all the people together. Again, I believe always in collective development. So let us move on to safety in a chemistry laboratory. So far I was mentioning about the QA, QC and GLP. Lab safety begins before we enter the lab. As I told you already, we should know what we are going to do. and we should have a procedure document. Then this is valid for all sorts of labs and is essential to carry out hazard assessment RAM before an experiment. Be it a regular experiment or be it a research experiment, we should assess what are the chemicals we are using, what are the what is the possible hazard associated with that. And always use protective gear. I don't know how many of the children are using. For sure, you will be using the protective shirt. Just give me 1 second time. There you go. Call Jason.
Engage him.
Hello, am I audible?
Yes, sir.
Sorry.
So carry on, sir.
So before we enter the lab, we have to know what is that we are going to do. Even in research, most of the experiments are routine, like preparing the solutions, measurements, etc. But let us make an hazard assessment and then only start the experiment. For example, after measurement, we have to save the data or spectra. That also we should have a protocol, how to name the files, etc., etc. So not only hazard analysis, entire QAC and documentation we have to make, then proceed. If there is a deviation right there, this is not followed, the new observation is made. Always use protective gear. This is the point what I'm telling. I'm sure all the people have lab coat and many people may not use gloves. I don't know how many people are wearing glasses. Yours is a big institute, maybe using. But to my surprise, in 98 or so, I went as an examiner for an MSc class. I was disgusted. People were mouth pipetting, right? So these things should be avoided. Protective gear is a must. Accident might still occur. Despite all these efforts, that is the thing what I want to convey. Accidents may occur, but we should be alert, identify, take preventive steps, and report to seniors. If you can solve, you solve and record it. If you are in doubt, report to seniors. Even after solving, report to seniors this incident, because this will tell the people that this is some small deviation that happened, right? So this is, I want to read everywhere I talk about this. I read quotes, unquotes, because there is a bit unparliamentary language, but that is quoted in a textbook I share with you. Safety and good housekeeping. This is the topic. Accidents are caused occasionally by design, frequently by bad maintenance. And the next one you just see, most often by somebody acting without prior. This is the issue. Oh, what happens? Let us see. Ho jayega. Something like that. So one Dr. Taylor, who wrote a book on analytical chemistry, he wrote it. That was in 1946, mind you. What is written, you just see. Fire and electric shocks are less hazardous than the carelessness and stupidity of the person. That word stupidity I don't like, but it conveys the emphasis. So I put in quotes and unquotes. So we have to be careful. That is the important thing. And we have to have prior thought about everything what we are going to do. Again, I'm telling, still accidents may happen, still deviations we observe. That is the life for research. Doesn't matter, but the major routine experiments and handling the chemicals, we should have a protocol. So we should give safety as the top priority. Combine this with good GLP, we will have all the things what we want to achieve, and cleanliness is extremely important. If you are looking at the minute quantities at detection level, unless your environment is clean, you should not even report. Yeah. So RAM, I already explained to you, recognize hazards. So safety principle and regulations in the use of chemicals we have to follow. Based on that, we can recognize possible hazards. And if that happens, what could be the associated risk we have to assess? and we have to minimize by adhering to regulations and prepare for emergencies. This is very important, that plan for emergencies and prepare for emergencies. That P covers both the things. Actually, it is planning and prepare for emergencies, very important. That is work complying with safety requirements. Means if such hazard can take place, these are the precautions we have to follow, and so on and so forth. So despite that, if it happens, still we have to be prepared. Planning is one aspect and preparing. So document everything before starting the work if it is not in the place. If it is in the place, just look into that once more. Follow it meticulously. Educate your youngsters. This is very important. Suppose a person joins for PhD, a teacher should not leave the person all alone in the beginning, right? Make him aware or her aware, and importance one should explain, and then only one should be allowed. So please remember RAM. I mean, most of you may be knowing it. And 5 steps for chemical safety are: know the chemical, that is MSDS sheet, I'll explain you. Labeling and storing is very important. If you are using a chemical or you are making a solution, you label it. And storing, there are certain aspects how to store. Suppose vapor pressure is increasing like styrene, you have to keep in cool environment. Personal protective equipment is very, very, very important. Now, unfortunate COVID made aware about, everybody is aware about PPE. Engineering controls, this is an important once a person moves into industrial production. And chemical waste management applicable to everything. Why chemical, only chemical industry? Waste management, taking from, starting from food preparation to cleaning and everything. Don't keep your house just clean and throw the waste in the street, right? We have to be concerned about everybody. So waste management in every walk of life is very, very important. One of the things, don't spit in the street. I don't know how many of you have visited BHU, Banaras Hindu University, one of the famous universities. And first time when I entered there in 1979, I stopped shaking hands with the teachers. I went as a very youngster to deliver a lecture. I told, no, if you are keeping the pan in your mouth, I don't want to shake your hands. Because people have a habit of rubbing it on the lips with the hand. So what I am telling is, one place I am telling, there are in Andhra Pradesh so many people chew pan, but I doubt whether everybody keeps hands clean. What I am telling is we should not spit in the street. We should not, we have to wash our hands regularly. Again, COVID has developed some GLP with all of us. We wash hands nowadays very, very clean. And so that is the, it's a 99.9% danger, at least 0.1% we got the benefit. So waste management, we have to have a plan, and we have to keep everything around us very safe, and chemicals definitely much more safe. So come back to the chemical safety. Suppose some spillage happens in the lab, right? So first and foremost is, if you are sure, evaluate the extent of spill and hazard, if you know, and immediately communicate to the lab in charge. If you are not in charge, isolate the area. Particularly, this is applicable where I worked, radioactivity spillage. If it is there, solution spillage, we have to isolate. Mitigate, if you are sure about the chemical and extent of spill, and mitigate it, but please never do it alone. Take the help of another person. Record the actions with details and date. Dispose all the cleanup material as hazardous waste, and report as per the Institute's safety order if something exists. For example, if it is acid is spilled, sodium carbonate or sodium bicarbonate you can use. If base is spilled, sodium bisulfite or citric acid you can use. But if it is mercury or hydrochloric acid, please don't do yourself. Take the expert's advice. So again, these procedures make available in records and train personnel. Now, what is MSDS? That is Materials Safety Data Sheets. Where do we get the information about chemicals. There are a few websites, and also all the details nowadays come with the chemical itself if they are hazardous, but on the bottle it will be written. And also the persons, big companies who are selling, they provide the customer service. And ANSI has prepared this MSDS hazards, and I'm sure all the faculty may be knowing. And you touch MSDS and name a chemical, you get the details. I'll show one example. Safety procedures you follow, and it also includes details on special handling, instructions how to dispose, and so on and so forth. 16 items it will cover. I will show the list. And also now, internationally, GHS, Globally Harmonized System of Classification, is made. And now they are called safety data sheets. But still, majority follow MSDS, because for SDSS also basis is MSDS, and people are used to MSDS. But youngsters start with SDS. And these are the items they cover. Identification, hazard. I will show one picture in the next one. Composition, first aid measures, that's important. Firefighting measures, accidental release measures, handling and storage, exposure control, physical and chemical properties. That anyhow, most of the people know before purchasing. Stability and reactivity, very, very, very important. Toxicity, 10 and 11 are very important. Ecological information, disposal consideration, transport information, regulatory information, and other information. Suppose for some chemicals, if such information is not there, not known, they say not evaluated, or they put a star and write that this is an information from a few labs, means that is not fully evaluated and accepted, so forth, so forth. Just see here, this is the typical sign of an MSDS. You get a label where health hazard is given a number. If the number is 0, it is a normal material. If it is 2, hazardous. If it is 4, it is deadly hazardous. Then you have to be careful. Then specific hazard, it will mention. Then you see the color code is important. Instability, this is the most dangerous thing. A chemical that is unstable, you have to store it properly. And it will, again, numbers are there. If number is there, it will have a violent chemical change. Number 3 means stock, and that heat may lead to detonation and may detonate on its own 4. If it is 4, at least please don't allow students. And like your quantum numbers, we write 4 quantum numbers: principal quantum number, azimuthal, and NL-MS. Like that, we have all these 4 numbers. Every student or every chemical, you practice this to write what is hazard number, what is fire hazard number, what is specific hazard number, what is instability. Once the 4 numbers are there, like quantum numbers, this chemical we have to be careful. You please develop this for 12th class students as a project. Let them take 5 chemicals and write these 4 numbers and label it with his name or her name and make a book out of it. In fact, I told in Rajahmundry, one college, and they have taken it as a project for MSc students. So better to, of course, they have gone into details. Better is at least these 4 numbers you make for chemicals. You ask students to make it and label them. Now, this is another pair of words. Like this, like always you have a confusion about contamination and pollution. People have terrible confusion. And everybody thinks anything contamination is pollution. No. Pollution, that contamination causes pollution is, that causes harm is pollution. Similarly, hazard and risk. The moment people think hazard means it is risky. No. We see the definitions. Hazard is a potential source of danger or harm. Means it has a potential. For example, potassium cyanide is associated with the hazard, but doesn't mean it will cause danger if you don't use it, right? But that hazard quality does not change at all. Whereas risk is the probability of suffering from hazardous material. Therefore, risk is equal to severity of hazard into probability of exposure. As long as KCN is in a bottle and stored safely, no issue. But when you are handling and if you touch it, then hazard, it becomes risk. So hazard and risk are two words which are related but not the same. Hazard is a quality, whereas risk is a quantity, right? Therefore, please be aware about hazard, minimize the risk while handling that particular chemical. Risk can be reduced by knowing level of hazard and preventive measures. KCN can be stored properly, or waste can be decomposed and disposed in a safe manner. And in fact, we did develop a method which I will share with you later. Now, as far as fire is concerned, there are a variety of fires. It can be a pool fire, a jet fire, a flash fire. All of you know the meaning. But the most important thing is if it leads to explosion, it will result in havoc. Means this will cause, this not only will expand, but it will throw out material. And if it is BLEU, that is boiling liquid expanding vapor explosion, that is the most dangerous thing, which will throw not only heat radiation, but it will throw the pieces into different places, can cause harm. And there are a variety of materials. If you see MSDS, there are flammable materials like petrol, right? And gases as well as liquids. Petrol is, of course, liquefied gas. This gas that becomes ignitable at 20 degrees and at 1 atmospheric pressure, and when it is mixed with air, if it causes fire, ignitable means it gets ignited, then we call flammable gases. And flammable liquids are the most nuisance. The moment you know gas, you are always a bit careful. But there are certain liquids which will lead to ignition or accident. It depends on the flash point. You all know that what is the meaning of flash point. There is the temperature at which a liquid, vapor is given off by a liquid and it starts getting ignited. Depending on the flash point, and in MSDS, flash point in physical properties is given for all the chemicals. There are 4 types of classification, and extremely flammable liquids, that number 4, that is that chemicals which have flash point lower than or equal to 23 degrees centigrade. And if boiling point is less than 35 degrees centigrade, together it can develop enough vapor which can catch fire in favorable conditions or unfavorable conditions if you want to use. Therefore, this extremely flammable liquids, one should be very careful. Right? There are 4 types. If it is number is 0, life is very safe. A safe liquid like benzene. Only from the heat point of view. Okay. Now, this fire tetrahedron, in fact, I have a few slides on thermodynamics. I will not spend on it. But let us see, you all know that if there is a heat source, if there is a fuel, definitely there is a possibility for ignition. And if oxygen is present around, in Telugu, Agnika Ajyam and Hava, right? Ee moodu kaliste, there will be a huge chain reaction, uncontrollable fire. So all these 3 materials, it is our responsibility to keep them at distance. Suppose some such fire takes place, all of you know that first thing is we have to put off the heat source, and prior to that, cut off the oxygen. How do we do it? By putting a carbon dioxide layer. How do we do it? By spraying the CO2. CO2 is fully saturated with the oxygen. So if it is sprayed, oxygen from air cannot reach the fire. So therefore, fire will slowly subside. And if you put off the heat, of course, then it will help. Don't throw water on the fire. Many people do that mistake. It will lead to more vapor. Many people do that mistake. And also in sand, many places like cinema halls, they keep carbon dioxide cylinder as well as sandbags. Sand also fully saturated with oxygen, SiO2. Therefore, it will form a layer which will cut off oxygen supply. So this is the way we have to understand the fire tetrahedron to utilize to cut off this chain reaction. Okay, and there are many types of fires. I will not spend time on it, but I have listed here extinguishers, pressurized water. Pressurized is very important, and from a distance, so that still it will be a bit of useful, but immediately nearby you don't throw water because it will cause more vapor and more gaseous, what I meant. CO2 is the best, one of the best extinguishers. Dry chemicals, okay, but one should know what they are using. And otherwise sand, a bucket of sand, right? All this can be used depending on the type of the fire, which I have listed here. One can read oneself. I won't spend time on this. Now, this is an aspect I want to spend some time. See, toxicity. This is another word which we should understand. The moment it is toxic, one need not be worried. What is that LD50? Also, I will explain in these 2 slides. This refers to the effect on living organisms. It's a measure of, LD50 is a measure of injury, that is damage to life or disturbance of biological function that follows exposure at some concentration. Acute toxicity is the one that produces immediate effects with just a single dose, like gulping the casein, and person will die simply, right? Chronic toxicity is the one which will contribute to the toxic effects, like poisoning of Napoleon through food with arsenic. That is slow poison, right? You know the meaning of it. Chromium-6 compounds are slow poisons. Benzene consumption is slow poison. Mercury is another example, whereas casein is acute. How do we measure? The quantify, we have to quantify. If we plot the amount, that is, dose means amount here, log dose versus the response, on whom it is done, definitely not on human beings, generally mice, mouse, plural of mouse. Mice are given this dose and it is followed. If 50% of the mice die at a particular dose like this, right? At 50% dose, if the test animal dies and 50% of, if the 50% of test animals die, and the corresponding dose is called LD50. Dose means concentration. That concentration that causes death of 50% of test animals is called LD50. The definition is there for both solids as well as liquids. Let me repeat again. If a test animal is given material, toxic material that varies, I mean, different animals are given with different doses, observe their survival, and if 50% of test animals die, and that corresponding dose is called LD50. Still 50% may survive, but the LD50 is important. The moment you know LD50 value from MSDS, try to deal with the materials much lower than that. Okay, now these 2 definitions I have given here. Lethal dose 50, that is expressed in milligrams per kg of body weight, and expect that mice, whatever way mouse behaves, we also respond in the same way.
Hello.
Yeah.
Hello.
Single dose of that material is lethal to 50% of experimental animals. Therefore, we have to be careful while handling with such chemicals. I'll deal with casein here, right? So let me complete the lethal concentration. For airborne materials, it is LC50. It is expressed in parts per million, and it is through inhalation. Other one is either through skin or mouth. And lethal concentration 50 is in ppm as a function of body mass. And if single dose kills 50% of test animals, then you call it as a LC50. For HCN, that is gaseous product of cyanide, 160 parts per million per kg is dangerous. Lethal means a person dies. Depending on dosage and mode of exposure, like oral, dermal, or inhalation, toxicity levels are classified as extremely toxic, highly toxic, and toxic. These data are available in MSDS for each chemical. And now we move on to green chemistry. What is green chemistry? Green chemistry is not a solution for everything, but at the same time, it is worth following. In majority of the cases, it helps. I taught this in 16 hours in a university, but again, favorable conditions only we have to take up. And in most of the cases, it is not that easy. But definitely there are cases where we can follow the green chemistry, but there are certain issues which are very important. Prevention of waste or byproducts. Atom economy. This is very important, but where do we get 100% atom economy except rearrangement reactions, right? So it is better to have the highest atom economy. Less hazardous chemical synthesis. Obviously, this we have to follow. But then there are certain issues where you need a hazardous chemical to be synthesized. Designing safer chemicals, good, ideal, but not practical. In every case, what I meant. Safer solvents and auxiliaries, this we can follow. Design for energy efficiency, this we should follow. Use of renewable feedstocks, wherever it is possible, we have to use. Unfortunately, people take a banana waste, a grass waste, a this waste, that waste, and think that it is universal solution. And in fact, hazardous material journal, I am a referee, believe me, 90% papers I send back to quantify them with proof, because it will lead to misleading facts. And reduce derivatives, this is an important thing we have to follow where it is possible. Catalysis, definitely we should follow because it saves energy, it increases the rate of reaction, and definitely a catalysis is an important thing. And design for degradation, and in fact people are following much before green chemistry. Design for degradation, this is the most important thing. You create a waste in your house, you clean it, is it not? Same thing we have to follow for chemical waste. We have to design a degradation policy and a method and follow it. And real-time analysis for pollution prevention. Again, pollution and environment contamination. Let us have clarity. Contamination is finding a material in an unwanted place. Pollution is the one contamination that causes harm to humans or environment. For example, if a teacher carries a chalk piece in his pocket, it is only a contamination. It doesn't do any harm. But if you touch sulfuric acid, it is a contamination and pollution. Please be clear. So we should have a procedure for real-time analysis for pollution and inherently safer chemistry for accident prevention. Definitely all of us follow, but we give more emphasis. So as far as the 12 principles are concerned, there are a few which are very good we should follow. There are a few impractical things, wherever it is applicable, we should use. So use safer solvents if solvent-free chemistry is not possible. Reduce volumes and amounts. This is very important. And in fact, in 69 to 70, when I was doing BSc, my teacher used to say, we should move on to microchemistry. And in fact, he made us to follow, to do experiments in very small test tubes. That is the approach we should have. Minimize hazardous byproducts. Instead of nitric acid or chromium 6, if we can use hydrogen peroxide, we should use that as oxidizing agent. Use less toxic reagents, but an industrialist may not agree because he or she is worried about output and profit. Use less toxic reagents, minimize waste. This is important to everybody. Design procedures, very, very, very important. And wherever it is possible, recycling we should utilize. This may be possible in a teaching lab, definitely, but not so easy in chemical industry. But we should have an approach that is pragmatic. So we should have a win-win situation. So what I am telling is study green chemistry to understand the issues and apply wherever there it is possible. But it is not a solution for everything. Reality is waste is generated in every lab. Unused chemicals will be stored, particularly in research labs, and byproducts will be produced. So what we do, how to dispose the chemicals? This is an important thing. So waste generation in different labs vary. For example, in a teaching lab, you may be dealing with hundreds of chemicals, large number of chemicals in small quantities. So disposal should be much simpler. Research labs need a few chemicals, but they are all need based, whereas industry, very large quantities are used, but a few chemicals are used. Therefore, you should have clarity about each chemical. You should have a document how to dispose the waste. It's a good practice to dispose of used chemicals and unwanted products daily, but it's not practical. So, but waste gets accumulated in many labs, including my own lab where I work. Plan to dispose of large quantities of chemicals safely that have been accumulated. That is an important thing. Okay. Now, in either case, it is essential to follow the standard operating procedures. But that first you have to make SOPs. Okay. Classify chemicals before deciding disposal method. This is, as I told you repeatedly, this is an important thing. Discuss before executing the method. Most of the people take it for granted that it is fine, we can do. No. We have to discuss, see the possible pitfalls, and then the last phrase you see, particularly we should know the fate of the end products. Okay, you degrade and don't throw them. You have to see whether it will interact with the soil. Suppose you are disposing in water body, whether it is harmful for the water bodies, or is it going to interact with the soil and move, migrate? So these are the things we have to think about, fate of the end products. So the most of the methods are neutralization, dilution, precipitate and store. Suppose you have few liters of material, just precipitate the quantity and rest of the solution can be joined to the wastewater, municipal waste. Convert to a less toxic compounds, which I will explain with KCM. Okay. These are the things we have to follow. Now, what we have done is, 1 second please. Okay, first thing has come. Okay, all right. I'll explain this first. I would have loved to explain the KCN and come to this. All right. Disposal of chemicals in BRC, over 50 years, tons of chemicals were stored. Most of them are innocuous. Somehow or other, they were not disposed. And a few places KCN was there. So I was instrumental in developing a procedure to have incineration facility, and fabrication was almost completed before I superannuated in 2015. Now it is in place and being used. Principle is very simple, but it appears simple on the projection, but engineering wise it is very difficult, cost us something like 4 crores, but it is worth it. So what we have to do is, all the material, we have to make it to undergo pyrolysis in controlled, with a controlled air supply at 850 degrees. We call it as primary combustion chamber. And whatever solid material, what we call ash, we have to have a tray below and collect it. And the rest of the gases are airborne particulate matter, both. We send it to the secondary combustion chamber, where we supply up plenty of the air until it undergoes complete mineralization, and there everything becomes oxidized. And very rarely you will be left with material that is not 1%, which again we collect. So both the ash compartments, once in a week we collect, and of course we dispose them in a different way. Whereas this completely mineralized gaseous projects, we send through another chamber where water will fall from here to down, whereas the gas will go up this way. Actually, this line will go from here to here. So just schematic. So what happens is, when airborne products and air goes upwards, even if the minute solid particles are there, they will be scrubbed down, what we call precipitation. And then rest of the gaseous matter will go to a chimney through a tallest building, taller than the tallest building of the environment. That is the environmental requirement. Then we have controls here to know whether we are releasing the products that are harmful or benign. This is the thing what we do at test level, did at test level, and at each stage we use the advanced instrumental techniques. Offline samples were tested. When everything was satisfied, then the fabrication was done, and now people are disposing large quantities of chemicals that are allowed. We made a list, and this is this is the principle of chemical incineration. First, convert, oxidize them under pyrolysis conditions. Not air supply is limited, but temperature is high. Increase temperature further, and total mineralization you have to do, allow it by air draft, high air draft. Then both the ash, that is solid particulate matter, is collected, whereas this airborne matter is sent from down to upward, and cool water is sent from top to bottom, so that the particulate matter, if any, they will be precipitated. Then that will be joined here, and the gaseous matter will go through a chimney, as I told you, to a tallest building. Chimney is the taller than the tallest building, and at each point there is an engineering control to know the product, and those indications were developed in the laboratory, and they're all available there in simple codes, so that even a 10th class operator can do this without much of deviation, of course, under the supervision. Now I will explain you, share with you what we have developed, a method for cyanides. There is no big research in this, but definitely it needed a bit of determination, like Mahatma Gandhi told, that is indomitable will, because 50 years people have stored, unfortunately, even potassium permanganate also, potassium dichromate also saved, which is fully oxidized and innocuous chemical. That is the fear complex. So that responsibility was given to me, and I said, okay, I will go through. So I started with a milligram quantity in a fume hood. What we did was, we have dealt with, treated this with the potassium permanganate, where this is converted to a less hazardous material. You see, the lethal dose is 5 milligrams. That means a person of 60 kilos body weight, if he consumes 300 milligrams in one dose, he or she will be out. More probably out, most probably. Now, this is converted to a material that is potassium cyanate, whose value is 841 milligrams. That means the same material, if one wishes to consume, he has to consume about 5,000 milligrams. That is 5 grams per kg total body weight. So this is less, this is fairly innocuous compared to KCN. That is the first step, oxidation. The second step, what we have done is, even this KCNO is a hazardous material, less hazardous but hazardous. So we dealt with sulfuric acid. So it becomes carbon dioxide and potassium sulfate, which is innocuous material. And for a regular students or juniors who may not be highly qualified, the color is the code. This will be the color when we deal with the permanganate. Until that color is reached, it takes few minutes. You have to wait, and you have to do in the fume hood, because in unfortunate conditions, if there is an evolution of gas, that will go through a HEPA filter, and it always airflow will be from the lab to fume hood to the filter. And here the color is like this. So we know that complete sulfur is converted to sulfate. But if you add the copper into this, the rate will be faster, and it will become copper sulfate. So potassium sulfate, copper sulfate, and CO2. So it is very easy. I don't know why people stored so long. And from 1 milligram, I have extended to 10 milligrams and demonstrated to people, then change it to 250 milligrams. And finally, I have gone up to 10 grams at a time in a fume mode. So if you have a storage, I told the people, if they have a kilogram stored in 10 rounds, that's about morning to evening, you can be finished. Now, these are the reactions. I may be taking 10 minutes. Is it okay? because we started late. Hello?
Okay, sir. Okay, sir. No problem, sir. Carry on.
Yeah. So I have only this Vizag's explanation, and then Bhopal I will avoid. So these are the reactions. Being chemistry students, potassium cyanide in presence of moisture or water, it will get more dangerous HCN. So this reaction should not be allowed. That is the first precaution in this conversion. And if KCN is treated with permanganate, then it will become, and after addition of that, water can be added or potassium permanganate solution can be added under suction. These are the reactions. Manganese dioxide is formed, that color indicates potassium cyanide. Potassium cyanide becomes potassium cyanide. Now, this when treated with H2SO4, it becomes potassium sulfate, ammonium sulfate, both are innocuous, and carbon dioxide, it is sucked through. And forward reaction of 1 should not be allowed because it is more dangerous. Its value is 160 ppm is lethal. In 10 minutes, a person will become unconscious and most of the people die. So for reaction 2, pH should be 12.5. In 12.5, this forward reaction doesn't take place. Okay. And reaction 3, when we move to next beaker, that should be at 1.5. So you have to make sure that there is no trace of KCN. At each stage, we have tested, and our testing limits, detection limits were 10⁻⁸ grams. Either electrochemistry or chromatography we have used, and both the cases we have established. Finally, we have handed over the procedure with the pH paper and color. So nobody has to go there. Foolproof it was made. It took about 30 minutes for the entire procedure. When we added cupric sulfate, in 10 minutes, 10 grams we could complete the decomposition. And this I felt very happy because this was lying there for 50 years. People started now slowly disposing of course lethargically. Now this work is in a few mode. This is myself. I told my younger colleague that if something happens, let it happen to me. So I did the work, and until it reached 1 gram, I didn't allow my younger colleagues to touch. They were only helping me in using the chemicals. I used the gloves and glasses, and in the few mode this reaction, all the colors we documented, all the pH we documented, a procedure is made. I felt very happy about this. Now let me quickly go through the Vizag gas accident, which you know. See what caused the leak in the early hours. Actually, I delivered a lecture in Rajahmundry within a few days of this accident. This accident made them to invite me, and I dealt with that. By the time decision was not made by the authorities, I mean that report, but whatever I predicted in Rajahmundry, they have come true. Again, without seeing the plant, without looking into the data, without looking into the sample analysis, purely based on GLP and QAQC, I could predict what could be the reason. This is experience and QAQC and GLP. So we can assess most of the things without entering the lab. There may be deviations. That's why I'm telling this is very important to follow QAQC and GLP. Okay. So let us go through this quickly because you have read enough in the newspapers. Monomer styrene is the starting material. They wanted to produce expandable plastics. That is their material. So COVID-19 lockdown, because of this, they shut down the plant. After all, in a chemical industry, they look at any industry, look at the properties. So they were in a hurry to open it. The moment it was allowed, they opened. Let us see the property. The boiling point is 31 degrees. So normally appears solid, but the moment temperature goes up, it gets liquefied. But as if you remember, you know the definition of vapor pressure. Whenever the ambient pressure is, vapor pressure is more than the ambient pressure, a material starts boiling, be it liquid or solid, whatever it is, right? That material starts boiling, right? So 31 degrees is too low for a solid. First, it gets converted into a liquid and immediately starts boiling if the temperature goes up. So it was advised that styrene should be, this is ISO condition, that it should be stored at 17 to 20 degrees centigrade. And you see MSDS sheet, they also write this 20 degrees. This caused a pressure buildup because this was failed according to the simplistic report. And so led to the buildup because so many days they did not maintain, that is, or it failed, whatever it is, because maintenance of the cooling system might have not been done. And that led to the buildup, has led to the breakage of wall, resulting in the gas leak. Simplistic explanation why they didn't follow. Even in the lockdown, these systems have to be checked. That is the meaning of QC and GLP. But was temperature control functioning? This is my question that I put. And later they agree that it was not working. Then why did you allow to open it? Before opening, that should have been checked. Is the standard operating procedure in place? They say yes, because it's an ISO certified industry. If so, was audit done? Important thing is before you start, all the procedures, whether they're in place or not, you have to check. And all the systems are working or not. That's called auditing. It has to be done. I am 100% sure it was not done properly. And vapor cloud spread when it was gas was leaked, vapor cloud spread, and various within 3 kilometer radius have been affected. 12 people died. Now they change it to 11. But people died. Even one life is important. What lessons did we learn from Bhopal gas tragedy, except making a book and SOPs? Now, what are the facts about this? This is from MSDS. It is a flammable liquid and classified as a toxic and hazardous chemical. Auto ignition temperature is 490 degrees. So let us not believe the stories. It won't ignite by itself. And 490 degrees, we ourselves won't survive. So, but flash point is 31. There is a spelling mistake. Flash point is 31 degrees. So, 31 degrees temperature, if the control goes off, in Visakhapatnam, you can imagine 31 degrees just like that we reach. In Andhra Pradesh, most of the places. So, temperature controls, whether they have failed or they have put up to save the power, we don't know. Combustion products are CO and CO2. This is the point I want to emphasize later. Fire hazardous. Open flames and heat accelerates flammability. So again, this is the thing. This heat condition surrounding ambient temperature might have accelerated the flammability. Explosion hazardous. Unless there is a mechanical impact, there is no chance for explosion. Unless there is a high temperature, there is no chance for explosion. So both the things might have taken place. Lethal dose is 316 milligrams. A 60 kilo person should have nearly 2 grams of LD50, styrene. But vapor is 9,500 ppm and 4 hours time is required. So vapor by itself is not that fatal. It will not lead to death. Something else might have led to death. I believe it was CO. CO is not fully saturated. Therefore, it will consume, it will react in that heat condition and dilute condition. It will accept oxygen or it will deplete oxygen. So people have become behooved, unconscious. This is because of this. And that has led to death because if it is along with, if you inhale vapor of styrene also, people might have died, whoever have died. But getting unconscious is this one. And also remember styrene molecular weight, even if it is airborne, in the path of travel, it will get precipitated. It will fall on the floor rather than reaching 3 kilometers. Therefore, I strongly believe this is the thing which has caused it. For this to produce, you need temperature. To have this temperature, cooling system failing. This is the thing, very simple thing, what we can understand. So potential acute health effects are, if irritant, some people face it, skin contact, irritant, and potential chronic health effects not well known. It is written not well known and we don't know. Ingestion do not induce vomiting. But vomiting was not, I don't think anybody reported. Storage, styrene should be stored in a separate safety storage cabinet. They have. This plant has. Keep away from heat. They were maintaining when it was functioning. Keep away from source of ignition. 100% they were followed. Keep container tightly closed. No. it yielded. And keep in, because pressure was built up, keep in a cool, well-ventilated place. I do not know. Nobody commented. Ground all equipment containing material. They might have followed, I don't know. A refrigerated room would be preferable. It seems they have. But then it was not functioning. And since for most of the, you have to use the material which have flash point less than 37.8, and everybody will follow this. Once we call refrigeration. So the question is, this is the line which was violated. Cool place, well ventilated place, and keep in tight conditions. These are all the things have failed. So that led to this accident. So how relevant are these data? See, styrene vapor is harmful, as I told you, but not fatal. Then how did people die? This I explained you. This is SIBO, right? This gas leakage from plant was reported on Thursday, that is 6th May morning, after the company tried to restart operations. See, one of the operators complained this about leakage, and somehow or other they did not attend. That's my guess, not guess, it was concluded. Did they audit SOP? Definitely not. Glitch in refrigeration unit led to gas leak. Official version that is, but it's a very simple. Why? Why it was not attended? Nobody answers. When was it identified? Post or pre-leak? I am sure it was post-leak, not pre. If it is pre, they would have attended. Overall, it appears that not only refrigeration control failed, but also there could be combustion and or oxidation products. Many samples were collected for analysis, and the report has come out later. That is in the next slide. I will show you. Yeah. Why it is going back? Just 1 minute. Previous. Yeah. See that report. Whatever report has come in the newspaper, I have copied. The unit in question is, and this is a huge report they made. I think 4,000-page report. The unit in question is an ISO certified facility, which means it has a protocol for everything. But protocols, did they follow? However, what seems to be the cause is that the plant management, in its haste to restart the plant, ignored the protocol of doing. That is the thing what I said, audit was not done. Much in advance of this report, I have explained of the plant before resuming operations. This combined with the lack of proper maintenance of storage, this is the major point. And faulty fixtures could have resulted in the accident. Nobody knows whether they, because most of the industries, they will not go for these cheap things. But anyhow, that is written, right, in the report. But I have a feeling it is mainly auditing was not done and cooling failed. But a pity, there is no evidence that we learned much from Bhopal tragedy. What is green in our memory even after 35 years? Even after 35 years of that accident, people have died because of MIC, methyl isocyanate, and isocyanate. We have not still learned. After Bhopal gas tragedy, many acts were promulgated, but that resulted in developing SOPs, emphasis on auditors, etc., etc. Are we following? Everything is there in place. That is why I said document it, but implement. That is important. Yet accidents are taking place. Human lives are lost. Does it mean that we don't have human life and environment we live in? We don't have a value. I am very sorry, but I feel extremely sad about these conditions. Right? Arresting a CEO may not help, but such industries, before starting, they should be told. If that happens, there will be severe action. Might have told also. Now, I feel our attitude is important. So your attitude affects my attitude. My attitude affects my behavior. It affects your attitude. Better is we have a good attitude so that about the safety, not only safety, general behavior. Therefore, we live in peace and safely. Particularly in COVID, let us learn these things and implement forever as long as human race is alive, because we have to live safe and healthy. And for that, we shouldn't contribute any unsafe conditions. So that's about my lecture. The safety ethic, I work safely, value safely, prevent value safety, prevent at risk behavior, promote safety, and accept responsibility. This is very important. Accept responsibility. And this always I show, and I used to ask a question. It's very, I'm very fond of this. Tirupati, that is pride of Andhra Pradesh. This is a nice church in Vienna I used to go. And this is pride of Punjab, Golden Temple. This is pride of India, Taj Mahal. Why am I showing? All four are clean places. I feel cleanliness is godliness. So follow cleanliness, follow safety, so that everybody will be safe. So always I give this title, this is summary. Though I write conclusions, it's always inconclusive because there is nothing to conclude here because it is continuous, as I told in the beginning. So to summarize, QA, QC, and GLP are very important. They are needed. Chemical safety protocols aimed at reducing and avoiding hazards, accidents, exposure to toxicity. This is very, very, very essential. They are aimed at reducing or avoiding. Reducing is definitely possible. There are certain cases which we can avoid. For example, while we're racking, we see a dirt, we definitely don't keep our foot in the dirt, right? That is avoid. Consult MSDS or SDS for chemical properties. Plan the path of the chemicals procured before storing them as well as after using them. This is important because we have to plan the fate of the chemicals. We shouldn't dispose them just like that. Making SOPs and following them is crucial. Making is important, equally important is crucial is following them. Maintaining records is a must. Green chemistry is good, but one needs to be pragmatic. Cleanliness is godliness. Above all, our attitude to safe practices and aptitude towards GLP, QA/QC are important. Bhopal gas tragedy and Vizag LG plant accidents, they are due to deviations from QA/QC and GLP and human error. Therefore, let us not repeat this in a small level or big level, but deviation is not good, harmful. Thank you very much. I thank the organizers for giving me this opportunity. These are the references, and I have sent this file to Vishwanath that can be copied. I don't have any objection. And I would like to thank the all authority organizers, Vishwanath Reddy, Krishnarao, my friend from Yogi Yamuna University, for inviting me. My younger colleague, one Mr. Venkatesh, who worked with me for KCN disposal, and he has gone through this article and gave critical inputs when I first prepared. And thank you very much for all of you for listening to this. Thank you. I'm open for any questions.
Thank you, sir.
Thank you.
Thank you very much for your informative and wonderful session. So I hope all the participants are enjoyed. And one of the participants, Mallikarjun, raised his hand. So if anybody have any queries regarding the topic, you can interact with the Reddy sir. So if anybody having any queries, please unmute yourself and interact with the speaker.
Okay, Vishwanath, if there are no doubts, if they get doubts later, my email is there. Let them write.
Okay.
Every Saturday I spend time to answer the queries. Saturday morning is for answering the queries. Every Saturday I spend time on it. Okay. Somebody has a question? No.
So till now, no.
At the time, yeah.
Sir, for that one more thing, I'm very apologize, sir, for before you entering into the session, I given your introduction.
About me?
Yes, sir.
Don't introduce also, it is nice. There is no need. See, they should know now, right? Okay. Actually, I am reluctant even to get introduced.
So nice session, sir. Many of us, those who are working in various sectors and various institutions, are very knowledge about their subject, but very few are aware and responsible about this chemical safety. So through your lecture, hope everyone will follow that. So we agree, sir. Your good laboratory practices are definitely related to internal honesty and integrity. Thank you, sir.
Okay. Thank you very much. Okay. I can put off my speaker and
Yes,
I
sir.
will listen a few minutes to the next speaker. My apologies to next speaker because I started late. And I completed also late, obviously.
Thanks, sir. So now, the next time, we are happy to invite another energetic and effective speaker, Dr. S. Raghupati Rao, sir. So here I am giving a short introduction about him. So Dr. S. Raghupati Rao did his master degree in from Andhra University, Vizag, and then he did his doctorate from IIT Madras. And in 2014, he joined as assistant professor in Rajiv Gandhi University of Knowledge Technologies. And he's one of the effective teacher and guided many projects for PUC and BTech students. And he also occupied so many prestigious positions. Among them, he is acting as a convener for Faculty Council at RGUKT-R, and he is also a president for Faculty Welfare Association. And he also working at different various challenging positions in the university as head of the department and coordinator for various academic committees. And he also worked as associate dean, and now currently is uh, working as a coordinator for scholarship section. Uh, and now currently he is going to give a talk on lithium-ion batteries is success story. So as all of we aware that in our daily life we are using lithium-ion batteries in so many portable electronic devices. And recently, in the year of 2019, the Nobel Prize from Chemistry given to the 3 scientists who worked on the lithium-ion batteries. So Raghupat sir also, he did his doctorate degree in metal oxide based cathode materials for lithium-ion battery. So now he is going to give his talk on lithium-ion batteries, its success story. So with this short introduction, I'm inviting Dr. S. Raghupati Rao sir to give his valuable talk.
Yeah. Thank you. Thank you, Nagaraj Garu, for your wonderful introduction. And I am Dr. Raghupati. And today I am going to discuss lithium-ion batteries and everywhere we use lithium-ion batteries and how it will be successful for a portable electronics. And a short introduction to the Nobel Prize shared by the 3 scientists last year, J.B. Goodenough at the left and Stanley Whittingham and Yoshino. These 3 scientists shared a Nobel Prize for the research in lithium-ion batteries and what are their contributions for the development of lithium-ion batteries and to get the Nobel Prize. Before going to the talk, we'll just look at the few basics of electrochemistry and we'll try to understand what is a battery. Then we'll try to explore why we have to gone for the lithium-ion batteries when comparing with all other commercial battery technologies available. Then we will try to understand basics and their scientist contribution to get the Nobel Prize. And outline of my topic is like this, and electrolytic cell and Faraday's laws and galvanic or voltaic cells, and what is the similarities and differences between a galvanic, voltaic cells or electrolytic cells, and why lithium-ion batteries attracted a more attention, then how to get a voltage for a particular electrode material, and how we'll calculate a theoretical specific capacity of a given material, and what are the cathode materials we will use, and the contribution of a Stanley Whittingham TiS2 as a cathode material, and good enough contribution is a LiCOO2. He explored that material as a cathode, and the next anode material, and finally we will discuss about a Yoshino contribution, complete construction of a lithium-ion battery. These are the various aspects will be covered in my talk. Start with a simple session, and we know that a electrolytic cell is the one. Here we will pass electricity through any chemical substance that electricity leads to the chemical changes. Here we are having a two metal rods. Generally, we'll call it as electrodes. If it is connected to the negative terminal, it's a cathode because it attracts cations, and it's a positive terminal because it's a here we are passing electricity through these. And if you are taking a acidified water, and it will become H plus and OH minus ions, and H plus ions attracted towards the cathode, and it will gains electrons, and hydrogen will liberates. Always at cathode reduction takes place, and anode OH minus ions attracts, and they will become a water and O2, and they will release the electrons. This simple phenomena we will call it as a electrolysis. Electrolysis can be determined, well explained by the scientist called Faraday, and Faraday's explained a few laws about electrolysis. That is Faraday's first law and Faraday's second law of electrolysis. According to the first law, the weight of the substance deposited at electrode or a gas liberated at a particular electrode is directly proportional to the quantity of electricity passed through it. Quantity of electricity, in turn, we can say that how much current passed for how much time. That is a current in amperes into time can be, we'll call it as a Q. So W is proportional to Q, W is equal to ZQ. In otherwise, simply we can say that W is equal to Z into CT. In generally, if we pass 1 ampere current for 1 second time, the weight of the substance deposited, we will call it as a electrochemical equivalent. And the Faraday's second law is concerned about if you pass same amount of electricity through two different electrolytes, the weights of the substances deposited are in the ratio of their equivalent weights. That is W1 by W2 is equal to E1 by E2. Here W is again ZCT according to the first law. You can say that Z1 CT by Z2 CT is equal to E1 by E2. Otherwise Z1 by Z2 is equal to E1 by E2. It's a very simple laws. Why I'm mentioning these laws, we will understand for the theoretical specific capacity calculations, we'll use the Faraday's laws. At that time, again, I will come back to this concept and we'll try to explain how we will end up with the theoretical specific capacity calculations. And a galvanic cell is the one. A galvanic cell or a battery, we can say that because it's a first invented by the scientist called Volt. So we'll call it as a voltaic cells. He kept a zinc metal in zinc sulfate solution, copper metal in a copper sulfate solution. He connected through the external circuit. Then the current flows from a zinc to copper rod, and zinc is getting oxidized, Zn become a Zn2 plus 2 electrons, and copper gains those electrons, Cu2 plus 2 electrons will give rise to copper. Reduction takes place. At anode oxidation, at cathode, reduction takes place. It's a spontaneous chemical reaction leads to the electricity. Where in a previous case in electrolytic cell, we passed electricity through that and it leads to the chemical changes. But here the chemical changes, whatever happened, that leads to the electricity generation. So this is what we generally call it as a battery. And a batteries, here you can see the comparison. The anode, which is a negative in the case of voltaic cell, because here the electrons will generate. But here anode is which attracts anions, it's supposed to have a positive charge. And cathode is vice versa. And they are having a plus charge in voltaic cell in case of negative in a electrolytic cell. So in primary batteries, we can say that either galvanic or voltaic cells are the primary batteries. A battery is simply, we can say that an electrochemical device which converts energy, generates in a chemical reaction or a physical reaction. We simply call it as a battery. And in between, we will use a solution called electrolyte. That electrolyte will passes the ions through that, and that part we'll call it as an electrolyte. Battery, already I have explained. The battery is classified into simply two categories: primary batteries. Primary batteries are the one just we'll use one time and we'll throw it. That is, once the chemical reaction, whatever the energy stored in chemicals is completely over, then the battery is not useful. The example, every day we will use a Leclanche battery. Where in case of secondary batteries is rechargeable. You can use n number of times. Once it's completely discharged, again you will charge again. That after charging, again you will take it back and you will use it, again you charge it. You will do it many times. We have a best example of lead acid battery, nickel cadmium battery. Nowadays, we are having smartphones and laptops in our hands. Every day, at least once in a day, we will charge and discharge the batteries. So the basic parts of any battery contains anode, cathode, and electrolyte. Anode, which oxidation takes place. At cathode, reduction takes place. And electrode, which is the medium, will conduct the ions through that. And why lithium-ion batteries have attracted more attention when comparing with many other battery technologies. Here we have a few points to discuss about a lithium-ion battery. Just go to the periodic table. What is the lightest metal we can get it from the lithium metal, periodic table? Hydrogen, helium, followed by the lithium. So we have the lightest metal possible metal is a lithium. And another advantage for the lithium is it is having a highest electropositive metal. And energy density. Energy density is concerned. So if you are taking a 1 gram of material, how much energy it can deliver. So that is a based on that we'll call it as energy density. Again, energy density is a volumetric and a gravimetric energy density. In next slide, I will discuss what it is. And voltage. And generally, whenever you use aqueous electrolytes, that means electrolyte which is readily soluble in a water or any other water-related electrolytes, the maximum voltage for that battery we can get is a 1.1 volt. And memory effect. So nowadays we are using a lithium-ion batteries. Even after 2 years or 3 years of usage, that means thousands of cycles charge discharge, we are getting same capacity over again and again. And there is no self-discharge. For example, you take in olden days, a battery which is used for the torchlights or any other batteries, if you keep some time aside, it will become a wet. That means the reaction is self-discharging and it's losing its capacity. But lithium-ion battery, you can use after any days, it won't happen anything to it. And long cycle life, as I already mentioned, we are using lithium-ion batteries for several years without any problem. Because of these advantages, lithium-ion batteries has chosen. Just now I will explain why lithium-ion batteries have more attraction when comparing with any other rechargeable battery technologies. Here you can take it's a later inverse, whatever later inverse. This is a volumetric energy density. On x-axis, there is a gravimetric energy density. That means 1 ml of volume, how much energy can be distributed, and 1 gram of substance, how much energy can be deliver. If you take a lithium-ion battery or a lithium metal or polylithium, all these are at a high end. They can deliver in a less value and less weight. They can deliver more amount of energy, especially for the portable energy applications. That means you need a device in your hands. In that, you need a battery. That battery has to give a more power to you. So obviously, you have to get more energy density. So because of that, lithium-ion batteries attracted more attention when comparing with any other battery technologies for a portable electronic applications. And like any other batteries, we are having a lithium-ion batteries also consist of a cathode, anode, and these two are separated by a non-aqueous electrolyte. Because here lithium is highly reactive with aqueous electrolytes, and we need high voltage, and that is not possible with the aqueous electrolytes, and we will choose non-aqueous electrolytes. Anode, generally we will use a lithium or a graphite, and where the oxidation takes place. And cathode, we are tried for a different materials. We are using either TiS2 or LiCOO2, LiFePO for materials for that. And electrolyte, we will use a 1:1 ratio of EC and DMC in a DMC solution, and that material used as a electrolyte. How we will construct the lithium-ion battery? Lithium-ion battery we will construct in a discharged state. So that's why whenever we use, so first we will use that as in a discharged state. The battery first has to be charged, then only you are permitted to use. any lithium ion battery. That's what whenever you buy a phone or laptop, first you have to charge it before switching on off the device. And charging, while charging, I will explain what will happen in the next slides and through the schematic representation. And we will use a current collectors. The current collectors provides a low resistance to the electronic pathways to the external circuits. What it means, I will explain in the next slide. How to calculate the voltage of a given particular electrode materials. Here you can see that this is the highest occupied orbital, and this is the lowest unoccupied molecular orbital. And the difference between these two, for example, this is the QC and this is QA. And the difference between these two, we'll call it as a open circuit voltage of a cell. This is the cathode material, this is the anode material. And here we have an electrolyte. That electrolyte must cover this entire region. This is supposed to have a less potential than the cathode. It's supposed to have a more potential than the anode. That means it is supposed to have a more potential window, because then only these cathode and anode materials don't affect this electrolyte that will be useful for your entire battery applications. The open circuit voltage can be simply taken as a QA minus QC by charge of a electron. And I will come back to this slide later. And how to calculate theoretical specific capacity. Theoretical specific capacity is, as per the Faraday's first law, 1 gram of equivalent substance can deliver 1 Faraday in 1 second. That we'll call it as a 96,500 coulombs. If we are taking the same material and you convert the units, that will take 1 gram of material can deliver 26.8 ampere hour. So theoretical specific capacity can be, if you want it, it's a 1 gram, but based on the molecular weight of the substance, you can get the theoretical specific capacity is 26.8 by molecular weight of substance, that is ampere hour per gram. For example, we will take a most successful cathode material, that is LiCOO2, and molecular weight of LiCOO2 is 97 grams, and take a 26.8 by 97 is a 0.274 ampere hour per gram. Generally, whenever you see your batteries, those batteries, the capacity will be appeared in form of milliampere hour per gram. So just multiply the value with 1000, then you will get the capacity value in a milliampere hour per gram. So this is about how we'll get a theoretical specific capacity. So how many number of lithiums taking place per formula unit can be getted as a observed specific capacity by theoretical specific capacity. Sometimes it may be more than 1, it may be less than 1. It depends upon what kind of electrochemical reaction takes place. So what is the cost determining factor in case of lithium ion batteries? And majority of the cost, you can see here, 49% of the cost of the battery will be depend upon the cathode active material. And the cost of 23% is contributed by the electrolyte, and anode active material having a cost of 11%. All together, and the battery, they are having a cost of the battery will depend upon the 70% based on the materials, and remaining 30% for the remaining manufacturing and other costs. So the battery cost mainly depends upon these materials. If you have a environmentally benign and cheap materials, we can have the cheaper lithium ion batteries and the safer lithium ion batteries for future. So what is the criteria takes place at cathode material? And what is the basic phenomena takes place at cathode material? A cathode, it must be a host for intercalation for a lithium. And if you take any solid substance, the maximum space occupied by the FCC or HCP structure is a 74%, and remaining is a vacant, void space, 26% is a void space. And you coming to the down, either BCC or simple cubic, there is a lot of space is vacant in case of any unit cell of a crystal structure. And as I already shown, the Fermi energy level of cathode must be very low. Because of that, we will get a high discharge voltage. And am I visible? Okay. And in case of host structures, we are having a different kind of layered structure, or the 3D channel structure has to be there. then you can find out the materials like graphite, titanium disulfide, molybdenum disulfide, nacicon, and these are the different materials explored as a cathode materials. And guest must be electropositive and electronegative and neutral species. Guest is our guest is a lithium ion, Li+, and host has to undergo redox process because lithium never comes in a form of lithium metal. It comes as a Li+. So automatically a plus charge is coming. There must be another metal has to adjust its redox value. So that we have to every material supposed to have that one element. It has to adjust its oxidation state. And what are the different cathode materials we are having? And LiCOO2. And on place of carbon, cobalt, we are having a nickel, manganese, and cobalt shared together. That is Mn one-third, CO one-third O2. These are having a 2D structures like layered structures possible. And spinal LiMn2O4. And inverse spinal is a LiMV4. And LiFePO4 is the most successful cathode material. And some network compounds, nacicon related structures, and like ferrous hydroxysulfate or Fe3PO4 twice OH twice, like a barboslite or lipsocombite. These are the compounds which is produced in our laboratory. Here, what will happen during the charge? First, have a charge. During the charge, we have a lithium here. Lithium like a LiCOO2 or LiFePO4, any cathode material that we are putting into the lithium side. See, that is lithium is coming and moving towards this, is deposited on the anode. And in a discharge, it's a free flow. Lithium easily can come out and enter into this material. So this is called a discharge. First charge is this, and discharge is this one. This is the charge curve, and this is the discharge curve. You are getting almost at a 4 volt for LiCOO2. This is the charge phenomena. During the charge, the lithium ions from any host structure will comes out and it will deposited on a anode. In a discharge, it's a free flow. Whatever the lithium ions present at a lithium anode directly will enter into the. So in case of charge, it acts like a electrolytic cell. In case of discharge, it acts like a voltaic cell. So first, different materials are there. So how to expose it? We are having all the advantages for lithium. Let us try for the materials which can act as a host for the lithiums. The best known material is a graphite. Graphite is having a layered structure, and the distance between the layers is almost 3.5 angstrom units. And so lithium can easily go and enter in between the layers. But the voltage of lithium metal is less than 0.5 volt. So, but we need a battery with high voltage. But here, whatever the graphite we are using is getting less than 0.5 volt. So now let us see at a periodic table, and we are having a lightest metal of lithium and different solid materials, and they have to find out. And the first chemist, Stanley Whittingham, tried a layered compound. A layered compound as like a TiS2, and this is having a layered structure. It's a TiS2 octahedra, and here we are having a layers, and there is a free space like a graphite. So lithium can easily go in, and it will become a LiX and a TiS2, and again it come back, then it will become a TiS2. While entering the lithium into the host structure, whatever the volume changes, it should not exceed 15%. If it exceeds 15%, what will happen? The structure will get destabilized and it will get collapsed. That means the host structure will not be available for us. So while guest species here is a lithium ions. While lithium ions entering into it, there must be a space between these things. This is the material is exposed by the Stanley Whittingham in the early days of lithium ion batteries. So here lithium ion batteries is exposed, but the voltage what we are achieved is 2 volt. Still it is very close to the whatever the lead acid battery we are using at that time. So later stages, you take a like a sodium chloride structure, whatever the TiS2 we are discussing. Each sodium is surrounded by the 6 chlorine atoms. So now sodium chloride structure is a Mx, and if you double it, and it will become a M2X2. Then I want to make this M and M dash two different metals, and one metal is a lithium. The other metal is having a, because I have to balance the charge, I am taking a cobalt. And halide here, whatever the anion, I made it as in place of halogen, I took a oxygen. They come to the conclusion of a LiCOO2. Here we are having LiCOO2 layered structure. This is a one layer of lithium oxide and lithium oxygen, and this is the cobalt oxygen layers. We are having a layer by layer. So we are having a layer by layer. This is the structure. These are the lithiums, and here we are having a cobalt oxide layers. And it's easy to lithium can enter in two-dimensionally and it can come out. So this is investigated by the scientist called J.B. Goodenough. And lithium can easily intercalate into the structure and it can come out. And well, coming to the calculations of capacity, and again, it's about 97. We are expecting the specific capacity of 270, but here we are having only achieved 145 milliampere hour per gram capacity. But it is stable over the 1000 cycles. Nowadays, whatever the commercial batteries we are using, that contains LiCOO2 only. So here, whatever the voltage we are getting is 4 volt. So it's very high voltage, and which is useful for all our practical applications. Now, how the chemical reaction takes place? LiCOO2, during charge, lithium will comes out from LiCOO2, and Li1 minus X will become, X lithiums will comes out. And whatever the cobalt here, 3 plus oxidation state, certain lithium is going out. So the X amount of cobalt has to adjust its charge to 4 plus for the charge neutrality. But the maximum lithiums can be removed up to the 0.5 lithiums. If you go beyond 0.5 lithiums, LiCOO2 loses its crystal structure and it will convert into different crystal structure. Finally, it's collapsing its structure. So again, during the discharge, it's gaining lithiums and it will become LiCOO2. The theoretical specific capacity, even though it's a 273, but we have achieved only 145 milliampere hour per gram. This is the contribution of a J.B. Goodenough. So he just changed the material and we are almost able to achieve very high voltage and capacity material for lithium-ion battery applications. So what are the applications we are using for lithium-ion batteries? So we are using lithium-ion batteries for all applications like mobile phones, laptops, electronic devices, and electric cars and space technology and all other technologies are lithium-ion batteries are used. So as I said, LiCOO2, we are only achieved 145, 150 milliampere hour per gram capacity. So still scientists tried for the different materials. It's 1990s LiCOO2 invention. Later cobalt is replaced by the nickel and manganese and they achieved the capacity of 180. In recent years, in addition to the nickel and manganese and cobalt, lithium also substituted in that site, and we are getting a almost 270 milliampere hour per gram capacity. And here we can see the materials. LiCOO2 is a layered structure, and spinel LiMn2O4. We can insert a lithium 3-dimensionally, and you can extract it. LiFePO4 only along the B axis you can insert and extract the lithiums in it. So charge discharge profiles of different commercial cathode materials you can see. LiFePO4 at around 3.5 volt, LiCOO2 is around 4 volt, and LiMn2O4 and LiNi.5Mn1.5O4 is around 4.8 volt. Different materials are exposed, and we are getting a different capacity values. So now we will try to move towards the anode. What will happen at anode? At anode, the criteria potential versus lithium metal should be very small because, as I explained, cathode has to have a high potential, where the anode material, if you want to replace by the lithium metal, it should be very less. And lithium insertion should be highly reversible and capacity should be high. These are the 3 criteria that has to be possessed by a anode material. What are the phenomena may takes place at anode? As like a cathode material, intercalation is possible. Because we are going for very low voltage, lithium can form a alloys with the metals like a tin and antimony. And sometimes if you use a lower voltages, whatever the materials you will use, they will convert into some other compounds, like a electrochemical reactions takes place. So what are the anode materials has explored for that? First, lithium metal is tried as anode. That what we call it as a lithium battery. And in the beginning of the slides, I shown something which is in a red color and unsafe. I will explain why lithium anode is unsafe. And intermetallic compounds and tin-based oxides and different materials are tried. And lithium anode, we are facing a few problems. At the time beginning, lithium as exposed as a anode, lithium is having a safety problems and cost of lithium metal is very high. And a passivating film is formed and this dendrite formation, you can see in the next slide. After few cycles, you can see in some images, there is a dendrite formation. Lithium metal comes out of the foil. Whatever the lithium foil you will use, it just comes out. And because of that, it's because we keep an entire lithium ion battery in a closed volume, because it has to be isolated from the our environment. So we will keep it in a sealed. Whenever you open a lithium ion battery and see it, it's completely sealed. If you are keeping the lithium in it and it's keep on coming and bulging, so it's because of that its volume increases and it leads to the accidents. So because of that, lithium is highly unsafe to use for the commercial applications. So we have to find out the alternative materials for a lithium ion battery. So later, as a beginning of the slides, I have shown a graphite. A graphite is getting less than 0.5 volt versus lithium. And it is having a layered structure. We can easily insert the lithium into the graphite and you can take it back. So 4 volt against the LiCOO2 and 0.5 volt, if you remove it, the battery versus contains which LiCOO2 and carbon or a graphite, we can get almost 3.6 volt. Whenever you buy a new mobile or laptop, you can see the battery is written, the voltage of the battery is around 3.6 volts. And here the lithium from LiCOO2 will comes out and enter into the graphite. And that again comes back and it will form a LiCOO. Here you can see lithium will come. So how it looks like. See, lithium will comes out, enter it into the graphite. And after that it will comes back and it will enter into this. And so the 1990s made a cell with a LiCOO2 and graphite, which is having a long cycle life, safety, and successful for many electronic devices. Once lithium ion battery got successful and it opens a digital revolution, and whatever the technology you are seeing nowadays mainly is possible due to the exploration of a lithium ion batteries. And you can whatever the digital mobiles or laptops and high capacity and cycle life of lithium ion battery is allowed to make it possible. You can see here a pictorial representation of a graphite here and LiCOO2. Both are having a layered structure. And during the charge, lithium will comes out through passing through the electrolyte and it will enter into the anode. After the discharge, the lithium which is present in a graphite, it will comes out and deposit over the LiCOO. So this is contributed by the Asino. And these three great scientists contributed. The first layered compound TiS2 is explored by the Steinle-Whittingham, but it's only giving a 2 volts. And the JB Goodenough explored a LiCOO2 and he made a huge increase in capacity as well as the voltage. And finally, Asino can able to use all these two materials and you can construct the successful battery, which is converted lithium battery into lithium ion battery. These three great scientists' great contribution made us possible to lithium ion batteries for a commercial applications. So what are the future direction in a battery industry or a battery research? So lithium ion batteries having a few availability of lithium is very low. Because of that, we have to find alternatives for lithium ion battery technology. So next to the lithium, we are having a sodium ion battery because if you go to the sea, entire sea is made up of with a sodium chloride solution. So we are having abundant sodium resources. But the problem with a sodium batteries is the energy density is lower, and it is useful for the stationary applications. And because it's a when energy density is low, you need a more space, and you need a more value. And still intense research efforts are going on with sodium ion batteries, and to get it use it for the cathode and anode materials. The other battery technology is solid state batteries, where the liquid electrolyte is replaced by the solid, which has to have a high conductivity for the transport of ions. Still many materials are exploring as a solid electrolytes. Maybe we will see very soon dry batteries as applications. Metal sulfur batteries, here through the just conversion reaction, a metal sulfur battery or a pouch batteries are exposing, and researchers are working on it. And we maybe in near future we will already in market. ISC faculty got released about a metal sulfur batteries, and they commercialized a few batteries in a Atmanirbhar Bharat. And multivalent ion batteries. A multivalent ion battery is like a more charge, like a copper 2 plus and Mg 2 plus. These materials, these metals also exploring as a batteries, magnesium batteries, copper batteries. But the problem is they are having a high charge. The movement is very low. So the next battery technology maybe is a metal air batteries. Metal air batteries works on a purely conversion based lithium oxygen batteries, and these are working. We will get very high capacity, but the cycling is the problem to address here. The next is a redox flow batteries. A redox flow batteries, we are having two different solutions, and they flow in a different paths. But here the crossover problem is there. Still, many scientists are working in future. But as of now, lithium-ion batteries are the most commercial batteries for the portable electronic applications. And I hope made you understand what is the contributions of these three scientists to make the most successful lithium-ion batteries and to made into commercial applications, and why they are eligible to get a Nobel Prize. And the talk of what we have learned today is we have tried to learn few basics, that is about what are the electrolytic and galvanic cells, and why we have studied about lithium-ion batteries and what is its importance, how to calculate a voltage and capacity of a given batteries, and lithium insertion and de-insertion in TiS2, a first cathode material for lithium-ion battery applications, which is invented by the Stanley Whittingham, and LiCOO2, a promising cathode material for lithium-ion battery applications, and lithium anode, which is replaced by the graphite as far the safety is concerned. Finally, we made a lithium-ion battery which is available for commercial applications. And you can see this is the coin cell we made, and this is the separator, this is the electrode, and this is, we'll call it as a coin cell. And we can use even Swagelok cell also. For our research lab, we use Swagelok as well as coin cells. This is the in situ XRD cell. And here you can see the glow box to maintain the inert environment for the fabrication of batteries before connecting to the charge discharge units. And thank you. And session is open for questions. If you have any questions, you can raise.
Thank you, sir. The session was very clear about the lithium-ion batteries. And I have a small query, sir.
Tell me, sir.
What is the cause for battery blasting, sir?
Battery?
Batteries are getting blasted.
Yeah. Especially in olden days, lithium-ion batteries, only we are used a lithium metal, that is lithium battery. Lithium batteries are the one where contains only lithium. And while we are using a lithium, that lithium comes out and it increases its value. If its volume increases, it will expand. But whatever the space given for the battery is fixed. If you are, it keep on bulging, it leads to the explosion.
Sir, what should be the ideal thickness of the separator in a coin battery, sir?
It's around very small. It's a micrometer size. It will use. It's a paper only, paper size.
Thank you, sir.
Thank you. Any more questions?
So thank you, sir, for your wonderful talk. I hope all of us every day we are starting our day with mobile, so that can power using a lithium-ion battery. So with your talk, we all understood what is there in the lithium-ion battery and how it works. And sir, we have a question. So even though the electrode potential is lower than lithium cobalt oxide, we are using lithium iron phosphate commercially. Why?
It's a safety. If you are going for the lithium iron phosphate is a state. You can see. Just go back to the slide where I have explained about LiFePO4. Yeah. Here you can see the voltage plateau is a very flat in case of LiFePO4, whereas in other cases it's having a solid solution flat. And the cost of the cobalt, manganese, and nickel are expensive when comparing with environmentally benign iron. So LiFePO4 is cheaper because any industrialist tries which is cheaperly available and cost-effective, economic, and you can make money out of it. So obviously they will use those materials as a commercial application. But still, LiCO2 and related materials are more exposed as a commercial applications rather than the LiFePO4, because LiFePO4, if you see it, it can only extract lithium in one direction, where in case of LiCO2 related, we can extract lithium insertion and de-insertion in two-dimensionally. Because of that, LiCO2 and related materials having more applications in commercial stage. But as per the cost is concerned, LiFePO4 is cheaper. And obviously, if you want to get a faster C rates, nowadays we are hearing about fast charge mobile battery. You can charge within half an hour. That means they are applying for the C rate of C/2. That means within an hour, they are inserting 2 lithiums. So you need that much speed. See here, you're having only one axis to enter into the lithium, but here we are having lithium insertion can be possible both the axes. So which is easy. So based on that, we'll use the either materials. Based on application, the scientists are actually commercial application, they will choose the material. Both materials are using, and LiCO2 related useful for the fast charging, and LiFePO4 material is cost effective, and where you need a slow charging rates, then you can apply for the LiFePO4.
So thank you, sir. Hope the doubt was resolved. And one more question from the same Dr. Bhaskaran sir. So he's asking which type of batteries have high energy density?
Obviously, lithium-ion batteries.
And one more question from Ratna Nitish. Which type of batteries are more useful?
What is application?
It depends on application, right?
Yes. So it's a portable electronics, it's a lithium-ion battery. And if it's a storage, we'll try for the lithium-ion, sodium-ion batteries. And even if you want a more capacity and few cycle life is enough, you can go for the metal air batteries. Metal air batteries, you will get 3000 capacity, but the problem is cycle life. We'll get only 5 to 10 cycles.
And so thank you, sir. And from my side, I have one query. So one more question, sir. Dr. Venkat Shweta is asking, what is scope of nickel cadmium battery?
Nickel cadmium battery is well established, madam, and it's already many materials are explored, and nothing much
So sorry for the interruption. The net connection of the speaker unfortunately disconnected.
Yeah. What is the question? Can you repeat again?
Sir, not audible, sir. So please join us. Yeah, please hold a second. So speaker will join. So hope you enjoyed the session. So lithium ion batteries are the most commercially successful batteries that we are using in our daily life, ranging from smaller mobiles, tablets, laptops. Even now, the lithium ion battery technology is exploring the transportation sector in the form of electrical vehicles and hybrid electrical vehicles. Hope they will commercialize and come to on roads soon. With the success of high energy density batteries. No, sir, not yet. Sir, you are in mute, sir. Please unmute yourself.
Am I audible now?
Yes, sir.
Okay, then. Can you repeat the question? I will get back
What
to
the
you.
scope of nickel cadmium batteries?
Yeah, nickel cadmium battery is a age-old technology, and most of the materials are explored for the lithium nickel cadmium battery application. And recently, no much work is going on nickel cadmium battery applications. And now, currently, whatever the future technologies I have shown to you guys, and much research work is going on these kind of materials, especially battery is concerned. You can follow this any one of these technologies, and these technologies are working, and many scientists are currently working on these materials.
Hello.
Thank you, sir.
Hello, sir.
Sir. So Dr. K.S. Kiran sir is interacting this week. Sir,
yes,
can
sir.
you...
Sir,
Yes.
What about magnesium, sir? Magnesium batteries?
Yeah, magnesium is they're trying, but the problem is charge and size, sir.
Okay.
For movement of a charge, because it's a 2+ charge. For example, you want to remove from any structure.
Okay.
As I said, the basic fundamental phenomena to be a host, the volume should not change more than 15%.
Okay.
And if you are taking a magnesium out, and the size of the magnesium is also big.
Okay.
And many people are working, and that's what will come under the multivalent ion batteries.
Okay. Okay.
And
so
the copper.
What about energy density in lithium ion, sir?
The energy density is very high, sir, because that's why it's a very highly applicable for a portable electronics.
Okay. Okay.
And volumetric energy density as well as a gravimetric energy density, both are very high.
Okay.
And I have shown in first slide in an.
Okay. Okay. Thank you, sir. Thank you.
See, what are the here you can see the x-axis. Is it audible now? You can see my screen. Yeah, now you can see that batteries for lithium-ion batteries, and here having a high and a gravimetric energy density as well as the volumetric density. And because of that, for portable electronic applications, that means lightweight and within a given a small volume and weight, and you can get a more capacity. Because of that, lithium-ion batteries are more successful in case of light battery applications. That is portable electronic applications.
Thank you, sir. Thank you.
Welcome, sir.
Thank you, sir. One more question from a student. Yes. Is there a better battery than a lithium-ion battery?
Again, we can't say that particular battery is the best battery for any applications. Based on your where you are using, application is important. Because if you are using a portable electronics, you need a battery which is having a light in weight, which is having a low value. Because of that, for portable electronics, lithium-ion batteries is the best. There is no question about it. But coming to the cost and commerciality, and coming to that, and you will use a different other technologies. So there is always thrust for knowledge. Scientists trying for new other batteries. Maybe very soon we may get a sulfur batteries, lithium sulfur batteries. But we are worrying about a cycle life. But still people are working on it.
Thank you, sir. And
Thank
it's requested to all the participants, if you have any further queries, you can we will share the mail ID of the Raghupati sir, so that you can interact with him. And for today, we are going to end the session, and we will come with tomorrow's session, and we will send the link and about the tomorrow session by this afternoon. So thanks for your active participation. So stay happy, stay healthy. Thank you. Thank you, Ananta.
Thank you very much, sir.